So last time we left off at chapter 7, part 1 at this slide. So now we're going to be continuing with chapter 7, part 2. So cycloalkenes can also undergo hydrogenation in the presence of catalysts, shown here. Cyclobutene and cyclopentene in the presence of hydrogen and platinum can generate cyclobutane and the cyclopentene. A ring makes a major difference only if there is ring strain, either because of a small ring or because of a trans double bond. Rings that are 5-membered or larger can easily accommodate double bonds, and these cycloalkenes react much like straight-chain alkenes. Cyclopropene has bond angles of about 60 degrees, compressing the bond angles of the carbon-carbon double bond to half their value. So here's a normal carbon double bond, 120. Now through the cyclic cyclopropene, you get an angle of 60 degrees. So as a result, this double bond in cyclopropene is highly strained. If we look at stabilities of cycloalkenes, in general, the cis alkene is more stable than the trans in small cycloalkenes. Shown here are some examples. Here's general trans-cyclic system in which you see the bond is trans. So here's trans-cycloheptene, and this is marginally stable. If we get higher, trans-cyclooctene, it becomes stable because we're getting more carbons in between. And then if we compare against trans to cis, again cis will be more stable. Small rings also have additional ring strain, and you must have at least 8 carbons to form a stable trans double bond. So this is where you get stability. And for cyclodecene and larger, the trans double bond is almost as stable as the cis. Brett's rule. So Brett's rule is in relation to bridge bicyclic compounds. Bridge bicyclic compounds cannot have a double bond at a bridgehead position unless one of those rings contains 8 carbons. Here's a bridgehead. This is just an example showing what a bridgehead compound is. This is not. In terms of figuring out whether a bridgehead molecule can have an alkene, here is a question or a problem. Which of the following are stable? We have A, B, C, and D. A is stable, right? This is a double bond that is at a bridgehead. This is not a bridge bicyclic system, and the trans double bond is in a 10-membered ring. As a result, it is stable. B is a Brett's rule violation, so we can cross this off, and is not stable. The largest ring contains 6 carbons, right? And the trans double bond can't be stable in this bridgehead position. Compound C, norbornene, is stable. It's a cis double bond, but it's not at a bridgehead carbon. Compound D, yes, this double bond is at a bridgehead, is trans, and it is stable because this bridgehead bicyclic system has an 8-membered ring to accommodate this trans double bond. So in terms of physical properties of alkenes, they often have low boiling points, and they increase with mass. The branch alkenes have lower boiling points. They're less dense than water, and they're slightly polar. The pi bond is polarizable, so there's an instantaneous dipole-dipole interaction, and the alkyl groups are electron donating towards that pi bond, so there may be a small dipole moment. If we look at the polarity and dipole moments of alkenes, cis alkenes have greater dipole moments than trans, so they'll be slightly polar. Boiling points of cis alkenes will be higher than the trans alkenes as a result. So here's an example of, for example, cis versus trans. Cis, again, you have the overall dipole moment going down. So again, here is just propene, and there's an overall dipole moment. When you have something trans, the overall dipole moment is 0. So in terms of alkene synthesis overview, you can generate alkenes through a couple of reactions that we've discussed. For example, E2, dehydrohalogenation. Through elimination or dehydrohalogenation, you can generate alkenes. You can do not only E2 versions, you can do E1 versions also of dehydrohalogenation, and you can lose HX. You can do dehydrohalogenation of vicinal dibromides, right? That's taking Br2 off, and dehydration of alcohols. So let's look at dehydrohalogenation by the E2 mechanism. So here's strong base coming in, plucking off the hydrogen, forming a double bond, and kicking off the X. It happens all at once. Remember, it has to be anticoplanar in order to do this. This is the transition state of which it's happening. Again, transition states have double daggers. And then you generate the protonated base, the alkene, and then the X, which is the leaving group. So again, this is happening all at once. So it abstracts the proton as a double bond form and as the X minus leaves from the adjacent carbon. Tertiary and hindered secondary alkyl halides give alkenes in good yields. Tertiary halides are the best E2 substrates because they are prone to elimination and cannot undergo SN2 reaction. For E2 reactions, bulky bases will actually favor E2. So here are great bulky bases: tert-butoxide, diisopropylamine, triethylamine, and 2,6-dimethylpyridine. If the substrate is prone to substitution, a bulky base can minimize the amount of substitution. Large alkyl groups on bulky base hinder its approach to attack a carbon atom, which is substitution, yet it can easily abstract a proton, which is elimination. The bulky base, such as potassium tert-butoxide, abstracts the least hindered H plus, giving the least substituted alkene as the major product, which is the Hofmann product. So we talked about Zaitsev, which gives the most substituted. Now there's a new terminology shown here called the Hofmann product, in which the least substituted alkene is generated. So here is an elimination potential from either this side or this side. This is not necessarily a bulky base. As a result, you'll favor the Zaitsev product, which is the most hindered, or not most hindered, the most substituted alkene, versus the Hofmann product. Another important thing that you need to remember is that E2 reactions are stereospecific. Remember, they have to be anticoplanar in order for the reaction to occur. So, depending on the stereochemistry of the alkyl halide, the E2 elimination may produce only the cis or only the trans isomer. So here's an example of a Fischer projection of a molecule. Then you can reconstitute it here with the wedges and hashed bonds. And so you want to rotate so that you can generate the H and Br in the anticoplanar form, and so you can then perform the reaction so that you eliminate and you generate the alkenes. And when you generate the alkenes, this generates the trans. So you go from an SR to a trans alkene. The geometry of the product will depend on the anticoplanar relationship between the proton and the leaving group, as shown here. So again, let's look at the stereochemistry of the E2 elimination. E2 reactions go through this anticoplanar transition states shown here. So you can look at it head on and look at a Newman projection of the actual molecule in which you see these are in anti-position to generate the alkene. This geometry is apparent if we view the Newman projection shown here. So let's do another problem. Show that the dehalogenation of 2,3-dibromobutane by iodine is stereospecific by showing that the two diastereomers of the starting material give different diastereomers of the product. So shown here, there are two. One is the meso-2,3-dibromobutane as well as the RR-2,3-dibromobutane. So in this case, the iodine, remember you want everything to be anticoplanar, will come pluck off the bromine, form the double bond, kick off the bromine so that you generate the transbutene or transbutuene. And then if you start off with the RR-2,3-dibromobutane, do the same thing. This time you get the cis-butuene. An important thing to note is don't try to memorize your way through these reactions. Look at each one and consider what it might do. Use your models. Again, I cannot emphasize it enough. Get your models. Use them to help you see these molecules. E2 reactions on cyclohexenes. So here's an elimination happening with this bromocyclohexane to generate cyclohexene. Again, when you're doing E2 reactions, it has to be anticoplanar, 180 degrees. And so the only way this can happen is when you have the hydrogen and the halogen at the axial positions. So here's the hydrogen and the halogen at the equatorial position, so then you're going to undergo a ring flip. So now that it's in the axial positions, now you can use it to pluck off that hydrogen, form the double bond, kick off the bromine. And if you look at it in terms of Newman projection, this is how it looks. So in order for this reaction to occur, even though this is more stable in the equatorial position, you need to undergo this chair-chair conformation in order for the elimination to take place. So here's another problem. Explain the following: deuterated 1-bromo-2-methylcyclohexane undergoes dehydrohalogenation by E2 to give only the indicated product. Two other alkanes are not observed. So here's the starting material, here's your base, and you're forming this, but you're not forming these other two. Explain why. So in an E2 elimination, the hydrogen atom and the leaving group must be at this transdiaxial relationship. So in this compound, only one hydrogen atom, the deuterium, is trans to the bromide. So when you draw this out as a chair conformation, so this deuterium is the only thing that's axial. The adjacent deuterium is also axial, providing a transdiaxial arrangement, and as a result, it'll pluck off that deuterium, kick off that bromide, generating the alkene, and not generating these. So let's look at debromination of vicinal dibromides. Vicinal means the bromines are attached to adjacent carbons. Here in the presence of iodide, sodium iodide, in the presence of acetone, you have plucking off of bromide, forming the double bond and kicking off all at the same time, generating your alkene. Again, the mechanism is similar to E2 dehydrohalogenation. As a result, it needs to be in this anticoplanar, the bromines. So it is a concerted stereospecific mechanism. So if we look at it in terms of a Newman projection, we'll take the bromine has to be anticoplanar, so it comes off, generating the alkene. Here's your alkene. So iodide ion essentially removes one bromine, and then the other bromine leaves as a bromide ion. Again, I can't stress this enough. Make a model of each compound, place it in the conformation where the groups to be eliminated are antico and coplanar. Positions of the other groups will be near their positions in the alkene products. For E1, again, it prefers tertiary, as E2 does, and secondary alkyl halides. In the case of E1, it undergoes carbocation intermediates. Rearrangements are possible. Weak nucleophiles such as water or alcohols are used for E1. And usually you have SN1 products too, since the solvent can attack the carbocation directly. So the E1 and SN1 mechanism, in the case of E1, first you have elimination of the halide to form the carbocation. Then your solvent will take off that proton and then quench that positive charge by forming the double bond. In the case of SN1, again you see formation of carbocation by elimination of that halide. In that instead of doing a proton abstraction, you're now doing nucleophilic attack so that you generate the ether. Dehydration of alcohols. So you can take an alcohol and under acidic catalysts and heat, generate the alkene in water. In general, in order to do dehydration of alcohol, you use concentrated H2SO4 or H3PO4 and remove the low boiling alkene as it forms to shift the equilibrium, because again this is under equilibrium conditions, and so that you can increase the yields of reaction. It is an E1 mechanism and rearrangements are common. This reaction obeys the Zaitsev rule. So let's look at an example of E1 dehydration mechanism. First thing is protonation. That's why you're using strong acid. This protonation occurs, allowing you to form protonated water. As a result, the water wants to leave and ionizes to the carbocation. Again, these are equilibrium arrows, and that's really important when you're looking at mechanisms. After the protonation, you have water come and pluck off that hydrogen, quenching that positive charge, forming the double bond. And this is a fast reaction, and it's just one arrow. So things that I'd like you to note is that here, all the arrows in your dehydration mechanisms have been out two ways, where it's equilibrium. This is a fast reaction, and so this is only going in that one direction. Important thing to note is that in acid catalyzed mechanisms, the first step is often the addition of proton, and the last step is often the loss of proton. So this will help you when you're doing your own mechanisms for exams or in class. So here's another problem. Propose a mechanism for the sulfuric acid catalyzed dehydration of T-butyl alcohol. So the first step is protonation of this OH to generate the protonated OH shown here. Again, you have equilibrium arrows. I just want to note that. Second step is ionization, and now you have the water come in and, oh, sorry, not the water come in, the alcohol come out. So let me draw that in. Sorry. So the second step of this is actually not shown here. You have deprotonation occurring. Oh, sorry, these two are mixed. So right here is the second step. So this is step 1. This is the step 2. So then you have the protonated alcohol coming off to form the carbocation. Again, this is an equilibrium mechanism. Then step 3 is the abstraction of a proton. So that's going to come, pluck off, and quench the bond. Again, this is going to be in one direction. So rather than, I'm going to cross that out, it's going to go only in one direction. So now I've corrected it. To form the alkene and protonated water. Catalytic cracking of alkanes. Here's a long chain alkane. In the presence of heat and catalyst, you crack it so that you generate the shorter alkane and then an alkene. So you generate mixtures when you do catalytic cracking, in addition to generating an alkene. Dehydrogenation of alkenes. So you can actually take just an alkane, and then in the presence of heat and catalyst, generate the alkene and hydrogen. Dehydrogenation is a removal of H2 from a molecule forming an alkene. It's the reverse of hydrogenation. This reaction has unfavorable enthalpy change, but favorable entropy change. So see, enthalpy is not so great, but enthalpy is favorable. As a result, you can have this happen. So in presence of a catalyst and heat, you can have alkenes being generated from alkanes. So this concludes the last reaction of Chapter 7, Part 2. And so I'll see you at Chapter 8.